Hmm. Okay, well, we're just going to have to go with this view. How do I go full screen? Control L. Ew, that's no good. How do I zoom? Okay, can everyone see this enough? We can zoom in. Go ahead. Who's got 11? Who has 11? Okay. We're explaining the work because we want everyone else to be able to go home and see what they're going to run into on this. All right, come on. If we want this to be productive today, we need people to be ready. So this is Group A. So who from Group A is going to come up and tell us? You just have to give us the gist, and I'm going to help you out too. All right? Out here, right there. Okay. Whoa. Go ahead. Everyone follow that? This, I'm assuming you're looking at the problem that, I gave you the list of problems. You're looking at number 11. This is the approach. This is correct. This is a very difficult problem, so pay attention. There's a lot that's going to happen in this problem. First thing was to rewrite it so look like square root of a squared minus x squared so that you could use a trig sub. Here's the trig sub. When you rewrite the integral, right, you get this, right? Okay, so explain to us what happened here. I mean, you don't have to go and say I canceled all this. Just explain what happens in the long run here. Let me help. Cotangent squared theta, there's a trig identity. Cotangent squared theta turns into cosecant squared theta minus 1. So this turns into cosecant theta, cosecant squared theta minus 1, and then they distributed this cosecant through to each one. So scratch this out. This makes more sense than this does. This is a little bit of a mistake here. This right here, the cosecant should go through to the cosecant squared and the minus 1 and create two new integrals. Y'all follow that? Now, we're also missing the 4/3. I'm not sure where the 4/3, maybe it came back in later, right? But does everyone see that 4/3 would have to be on both integrals? Okay, so explain now what the issue was here with these two integrals. And let me interrupt. This was a pretty big leap right here to go from the cosecant cube to know to split it to cosecant and then cosecant squared, and then use the cosecant squared as the dv and use the u to be cosecant and do your table on integration by parts. That's not necessarily something that would have been automatic, so that took a little time. Was there a comment? No? Yes? Mm-hmm. The secant cube works out a little nicer than this one because, as we'll see, when you do this, right, and here's your integration by parts, here's your ultraviolet minus voodoo. Go ahead, you can pick up where I'm leaving off here. What about this voodoo thing that you get in your new integral? Well, up here, right? Notice this up here is actually what you have down here again. So you have to turn that cotangent squared again into another cosecant squared minus 1, distribute your cosecant through, and then your cosecant cubed appears again on the right side. So you've got the cosecant cubed on the left side, then you've got minus the cosecant cubed on the right side, and so you'll be able to move it over. Right? Okay. So you move that over, and then once you get that, that was ultraviolet. Yeah. Okay. That's good. You can have a seat. Good job. That's what I'm looking for. Okay. This problem's not even close to being done, right? Because what has to still happen now is what? Oh, your thetas have to go back to where they came from. Did y'all do that or not? Yeah. Okay. It's on a different page. So just to backtrack, okay, because this is one of the more challenging problems. All of this trig sub turned out to be this right here, right? This turned into be a pain in the ass, and it splits up into two different integrals. One of them's easy, one of them's going to require integration by parts. There's your integration by parts, but it's the integration by parts where you're pulling the rabbit out of the hat, where it appears again on the other side. So then you resolve what that integral is. Once you resolve all that, you plug it back in, find your thetas, and you're off to the races for the answer. Now, I will post the full solution to this, done correctly. There might be little mistakes in here. It might be hard to follow, but I'll post that later today. I've gone through the first 10. I haven't finished it. I'll have those by the end of the day. Okay? All right, any questions on this? The main point here is just so that when you go to practice these on your own, the ones you haven't done, you can see how these groups attack it so you're not wasting that time. All right? Who's got 12? Which one? Yeah, I don't think so. Let's see. What does 12 look like? There it is. Okay. So, what sort of issue did he run into with 12? Nat? Yes. Ooh. Oh, I'm not disagreeing. I'm just saying, ooh. Okay. I haven't done this one, so I guess. So chain rule there, right? Chain rule. Hold on, let me back you up. The chain rule gives you, so we're trying to think of why this is going to work, right? When you take the derivative of this, the chain rule is going to spit out the 1 over x. And by the choice of dv being dx, going backwards up to v gives you what? X. And that x, when it multiplies across here, voodoo, is going to cancel, which is going to leave you with the natural log of x squared. So what you, in effect, you've done is reduce the natural log x cubed problem to a new integral of natural log x squared. And if you repeat it again every time you do it, it's going to keep coming down. Right? Very good. Let's move on. I mean, you're good. You're good. You can have it. You can have a seat. Everyone clear with that? That's good. Excellent. That's what I want. All right. No questions on that? Yeah, that one worked out nice. Okay, 13. So 13 should be our next group. This should be like a public speaking class. Y'all are doing so well. Where's 13? What kind of papers? Oh, there it is. All right. So was 13 hard or no? Eh? Kind of a pain in the ass? Okay, go ahead. Why? Okay, so you had rational function, polynomial over polynomial, degree on top is bigger than bottom. Go ahead, long division. You're happy with all that? Okay? All right? Okay. Oh, so the denominator factored. Oh, that made it nice. So you factored the denominator and then created the two, what, linear, A and B on top. Okay. Keep going. Should I scroll down? How did you solve for A and B here? So you did the shortcut. Okay. And it worked in this problem. Looks like my copy did not get that included there, but you can see it here. Okay, so that was the antiderivative of these two. Where's the 4? Right, that's 4. Antiderivative 4 should be 4x. Okay, so missing a 4 here. So if this problem was worth 20 points and you missed the 4 there, I'd only take off like 18 points. No, I'm just kidding. Now that'd be something I circle and I wouldn't take off for normally because you have it here. You just like forgot it here. To me, that now if it keeps happening in the test over and over and over, you keep making these mistakes. At some point, it's going to cost you. But you following me? Okay. All right. So these two were. How'd you get to these? Like how'd you get from here to here, here to here? That's just obvious to you now? Okay, hopefully that's obvious to everyone here. You have a constant over a linear expression, constant over a linear expression. You pull the constant. One thing you have to pay attention to is the number in front of x. In both of these, it's 1, so you don't really have to factor that in at all. That looks good. Other than the 4, does that look good to everyone? Yeah? Trusting all that works good? All right, good. Wow, man, this is awesome. Yes? Yeah, let's just pretend for a second that this was negative 4 over 2x plus 3. The first thing I would do is come in here with the 1/2. That would take care of the 2 in front of the x. Then I would do the negative 4, and then I would do the natural log. So the 1/2 in front would basically make that a negative 2 instead of a negative 4. That make sense? If this in front had been a negative 5, then I would have come in with a negative 1/5, and then I would have had the negative 4, and then that would turn to 4/5 positive. That good? When you do what? Multiply everything by? Not necessarily 8. I just remember there's a problem like that. Well, that's a great question. See, because what we did, when we did the first time I ever showed you the massaging where we kind of made the top look like the bottom, the derivative of the bottom, we were doing that when we could not factor this. See, but when this factors, then you should be able to come up with an A and B that should produce this. So when it doesn't is when you need to let u be the bottom, then try and make the top look like the derivative of the bottom, and then eventually you're going to have to spit one thing off and do a completing of the square. I'm sure one of these is going to do that at some point here. When you cannot factor the bottom. Say it again? You're trying to make the top look like du. Okay, where are we at? 15? 14? Dun, dun, dun. Is that 14? No, that's 4. Was that 14? Oh, there it is. All right. So what happened with this one here?
This is basically just like the other one. Back to the bottom.
Shh.
Clear the fractions, multiply it all out.
Could you use the shortcut on this one? Okay. Yeah, so the shortcut is, you may be able to do it. It's going to be kind of tedious if you do the shortcut because you can never kill off A and B with at the same time, because you can't make x squared plus 4 0 ever. So can I go back here? The x to the 4th minus 16, you factored that how? So a difference of squares first, and then after that, one of those is another difference of squares, correct? Okay, everyone okay with that? All right, so that gave you 2 linear factors and 1 irreducible quadratic factor when you factor this bottom out. So you do your a over linear, b over linear, cx plus d over your quadratic. All right, so you did all this, expanded that out. Okay. Is this it here?
Well,
yeah. Yeah, that's the set of linear equations, right?
Yeah.
Okay.
That's how we get it. And then on the last part, it seems like that's correct, except for the x squared plus 4 should be the inverse tan.
Arctan, yes. Well, let me see. Where was it? It was this, yeah, because this turns out to be, what constant is there? Negative 1/16? C is 0 and D is, yeah, so D is going to be a constant here. And so you have a constant over u squared plus a squared, and that's going to be the arctan formula. Okay, I agree. Does anyone have questions on this? Yes, go ahead.
Okay, so this, I was getting stumped on a problem Tim was giving me homework. I was getting confused on what I'm actually supposed to use. Say, could it be dx plus c or dx plus d? Do we end up using that when we have an irreducible quadratic? That's when that comes into play?
Yes. If you're doing partial fractions and one of your factors from this is an irreducible quadratic, then instead of putting just like a over it, you have to put a linear expression over it. So, yes, what else?
Did you have to use partial fraction decomposition just for this one, or could you use arctan?
I'm glad you asked. Arctan won't work. The reason why is because this doesn't look like u squared plus a squared. Now it does look like kind of like a u squared minus a squared, which there is a formula for. It's and that's one thing we want to talk about today. I'll show you when we get to the other problems. That there are more formulas to handle if you don't have a squared plus u squared. There's a formula for a squared minus u squared and u squared minus a squared, and they're on your formula sheet, and they're right there. Number 17 is the arctan one. 19 and 20 are the other 2 variations. So you need to be aware of those. All right, I'll show you in my work that I'm going to do later. So I don't know if I answered your question, but y'all are good. I'm curious, this little thing here, did y'all come up with this on your own, or was this something that's how you just made sense to you? Okay. So figure out what the coefficient of x cubed is here. There is no x cubed on this side, so that must be equal to 0. And then you just looked at all your coefficients of a, or on x cubed. However you want to do it, okay? The reason why I show it to you that way is I want you, the way I show in class, I want you to see that if the left and right hand sides have to be the same, then the coefficients have to match. That's the only reason I do it that way. But if you're happy with this, go with it. Well, you need to be able to solve a system of equations. You can do it by hand because you all took college algebra. But the efficient way is to use the calculator to do it. Now, there was only one person right without one? Yes? Yes. So I'm willing to loan you one for the test. I'm not going to make you go buy a calculator because this is the only time we'll need it, all right? But you need to learn how to use it. I still haven't made the test, so I don't know. I wanted to see how this went. The level of these problems is medium to hard. Some of them are real easy, but some of the problems are medium to hard, and I couldn't give you a whole bunch of those in an hour, 40 minutes. So it's going to depend on the type of problem I give you. Yeah. So. Well, who's next? What is it? That was 15? Who had 15? This group? Let's see if I can find it. Okay, so 15 was, what's that? I can't really read it, but I think everyone can. I think everyone can look at see what's going on at least.
Okay, so we factored an x squared over here. We got x squared times x plus 3. And then we did the a over x plus 3, b over x, and c over x squared.
So this is partial fractions, right? You did not have to do long division. And when you did this, why did you put b over x and b over x squared? Yeah, this is a repeated linear factor. Could you also look at it as a quadratic factor? If I'm just getting you to think a little bit here, could you look at it as an irreducible quadratic factor? If it was, then could you write it ax plus b over x squared? I mean, that's what it would be if you did an irreducible quadratic, right? Split it into 2, and what would you get? A over x plus b over x squared, which is exactly the same thing you're getting by doing it that way. I'm just showing you that it would have worked both ways. But you're looking at it as a repeated linear factor. So for each one, you have to write a letter over the factor, the letter over the factor squared, and then so on until you get to the highest power. All right, go ahead. So now you set up. Okay.
Well, I factored mine out, so I got ax squared plus bx squared plus c 3bx.
Well, y'all didn't do matrix, did you?
You could have.
Yeah. Yeah.
I did sort of.
You did the matrices? No? Yeah, this is the shortcut, isn't it? This is the shortcut. Trying to figure out what A is? Or no, what did you do first? You found out what C was first. So you let X be 0 to kill off both of these. 0 on this side gives you -3. 0 here gives you just 3C, and then you solve for C. Then they let X be -3. That would kill off these two terms. That would let them solve for A. And then letting X be 1 kills off nothing. Okay, so that worked out. All right, so look, you could do this. You could do this either way. This might be hard to do with the shortcut unless you're really comfortable with it. Yeah, but the matrices would definitely work for that. Is that the way you did matrices? Okay, but you get the same results. And once you get these answers, you have 3 pretty basic integrals, right? First one is going to be a natural log, right? Oh, here it is. There it is. And then this is a natural log. What about this one? It's just like x to the negative 2, so power rule. Any questions here? Yeah, that's kind of, I get a lot of students that do that. They see 1 over anything, and it's automatically natural log, but it's got to be linear down there. Yeah. Okay. All right. So that takes care of 11 through 15, right? How about 16? Was 16 hard? You got it? Okay. Let me see where 16 is here. All right. Well, hold on. Who from your group has not come up? You haven't, right? All you have to do is stand up here. You don't have to say anything. You just have to stand up here. It's participation. You want to do another one? You want to do a different one? You had 4 of them, right? You had 1 and 6? Okay. Well, you can stand up there anywhere. You know, moral support. Okay, 16. Go ahead.
So this was pretty straightforward. You're doing partial fraction. You have first you have the repeatable x minus 1 squared, and then you have the unreducible quadratic x squared. So that's what you do. Cx plus b. You break it up. Your x squared minus 1, and you bring it through. Then you distribute your a and your b, and it just loads up. Then I separated your x cubed, x squared, x, and then the constant. Plug it into a matrix. Found your values a, b, c, and d. Came out pretty nicely, negative 1, 1. From the back into the problem, simple integration of 1 minus x1 squared, and then
That's this one.
yeah, that's that one. And then 1 minus x1 gives your 1.
This one right here.
Gives your ln x, and then this minus x plus 1. I actually broke that up into 2 different intervals, so it's minus x over x squared plus 1, and then 1 over x squared plus 1. And you'll realize that 1 over x squared plus 1 is just tan inverse of x, and then x over x squared plus 1.
Basic substitution.
Will give you 1/2 ln x.
Yeah. Okay, that's all good. I need to double check the numbers, but that all looks good. Any questions on the attack on that one? The very beginning?
Yeah, that's a great question, because you already have them broken up.
Yeah. Now, you didn't do long division.
I didn't have to.
Okay, why didn't you have to?
Well, the highest power is squared, and it's x squared.
Yeah, so it's obvious that the power on the bottom is bigger. Okay. That all looks okay. Very good. I need to take attendance. Who still needs their clicker? Anyone need their clicker? I haven't turned it on. Hold on. Go ahead. Okay. We good? So I have a question for you. I would like a reply. I'd like you to give me your feedback on right now. Do you feel like us doing this is constructive at all? Like just vote. Tell me yes or no. And I'm not going to show you the results. That way you're not influenced. Doing it this way, going through these, should we keep going, you know? All right? Yeah? Okay. So some people don't think it's useful. Fine. Okay. Now, let me ask you another question. Don't reply yet. I haven't asked the question. A. Okay, so let me ask the question. Do you think it was good that I put you in groups to do this? Like, do you think that that helped you? Okay. All right. So again, we got one or two people who don't like people. No. So I think that there's some value in this. As I started to go up through the higher level courses in math, what I found was that there was like a core group of us that we always got together, and we registered for the next classes together. We stayed together, and it helped. Because we would get together, but we would do it for everything. No one would have to hand us a review. Like if the homework assignment, that's what we did. We each came prepared with our portion of the homework, and then we explained it to each other. And that was the key. We were able to explain it to each other. And so, if you get into that habit of not only doing the work, but then bringing it to someone else to present, that really shows that you understand what you're doing. Now, what you need to be ready to do by Monday is be able to present every single one of these problems, right? Not just the one you needed to do. You need to understand all of them and be able to explain those. If you're at that point, then I think you'll be ready for the test. There's never any guarantees. With Cal 2 integration, I'm going to put a problem on there, and everyone's going to get pissed off and say that I was making up some new problem, but it's really just the same. It just maybe doesn't look exactly like one of these, and so you get all mad. But the principles are all here, right? Techniques of integration are all in place. What else? Okay. Yeah, so you can have the formula sheet, right? The 6 sheets or whatever, you can have that. You were also allowed to write 2 formulas on that. No, power reducing is on there, right? The natural log, the integral of natural log can be written on that. And what? Secant cubed, yes, that's right, secant cubed. So that you can have. Don't have other stuff written on it. Don't show up with your unit circle from pre-cal and say, hey, I've always used this on my test, because I can't let you use something that someone else doesn't have. It's just not fair. Then I will provide you with the trig substitution stuff. Remember the 3 different cases for trig sub? In your notes, they were in boxes in your notes. I will provide you with that. What else? I don't think you need anything else. Formula 17, well, that is what you print out and bring. Yeah, look, I'm not going to, those 6 pages, where are they? Do you have them right here? Can I see your 6 pages? These are on the web, in Canvas, under Files, says Formulas. You must print these off. You must bring these. If you don't have them, you don't have them. You don't get to use them, all right? I'm not going to provide them. Okay, let's move on, because I think we need to keep doing some more problems here. That was 16. What's up next? Should we start back at 1 now? Oh, 1 was kind of tricky. So who wants 1? And when you start to explain this, can you explain why it just doesn't go clean initially, or what? I would like to hear the things that you didn't like about this when you first looked at it, like if anything stumped you.
So first off, we have the cube at the top and the x at the bottom. So first off, I just pulled out the 3, which left us x in second, 1 plus x in sixth. Realizing that we need to do some new stuff, we immediately pulled out some x cubed times 2, which is still x sixth. Then, for u substitution, we just use the u cube, x cubed. We got 1 over 3 du. Just wrote in wrote in the u, pulled out the 1 over 3, 3 over 3 equals 1. So we left with 1 over 1 plus u squared. Realizing that looked like arctan, just wrote it down and wrote u over u. Substitute as x
Okay, now let me ask you, why would you, or how did you see that you were going to need to rewrite x to the sixth as x cubed squared? Like why? I'm not sure if that's necessarily a natural thought.
Well, x6, and there's not a whole lot we can do with that, but we did see an x cubed at the top, realizing that we could have used us, we just have to play around with it.
Okay, so you said x cubed. I think what you meant is you see the derivative of x cubed up top, right? You're seeing the derivative of x cubed up top in having an x squared up there. But then you would have to somehow manipulate that x to the sixth to incorporate the x cubed that you want to use for u. And if you see that little light there, if that comes through, the whole problem becomes almost trivial, right? Because the u substitution that works takes you straight to arctan and you're done. All right? But I can't really teach you how to do this part. I can just show you that it's possible. You know, that sort of thing can happen. So you have to try something. Okay, good. Thank you. All right, number 2. We're number 2. So I'm looking for people who have not, did I pass it? People who have not gone up. Which one? Further? There we go. No? I'm going up. That's 11. Look, these are not in order. They're in order of groups. So this is the first group stuff. Yeah, I know. Yours should be this one coming after this. No. Y'all didn't turn anything in. Everyone gets a 0. There it is. Oh, okay. So y'all were stumped on this for a while or no?
Knowing that d and u is cosine x dx, it all comes out nicely. L and u du, and then integral L and u is u L and u minus u is the formula he gave us. Plus the put u back in cosine of x.
In fact, the formula I gave it to you. You're allowed to use it, but we showed it in class. We did that in class, right? Okay. Is that right? Minus sine x, yes. Okay. All right. So 3. Ah, yes. So was that like, did it take you a while to get to that? No? It was, so what made you go that route? Okay. So after seeing enough of these, you realize that, because du is not really there, right? I mean, it's there, but the x up here is an issue, slight issue. But I'll let you keep going. Go ahead. What's this, though? What's here to here? What's that? Okay, so up here you took this and solved for x, replaced this x with u minus 2. Okay? Well, what about from here to here? Split into 2 fractions, right? This over this, this over this. Rewrote them as powers so that you could employ the power rule. Plugged in your u. Yep. So, I mean, the key to the whole problem is that the substitution of x plus 2 is going to work. And if not, it can become ugly. Was there a question? Yes.
Can you just square the whole thing and get rid of the square root on the bottom and then divide?
Square? What do you mean square?
Square the whole thing to x squared over x plus 2.
That's a great question. You're done, sir. You can have a seat. Thank you. That is that is a great question, and here's the problem. Okay, if you have a function, okay, and you're trying to integrate this function, and you want to come in here and square it, that's fine. But then you have to square root it because it's not the same function anymore, right? If you take something and square it, it is no longer the same thing. If you have an equation, you're free to square both sides, correct? This is an expression inside of this integral. So if you want to square a function, great, but then you have to square root. So you might simplify it a little bit by making it x squared over x plus 2, but you have to remember that's still sitting under a square root. And you can't pull that root out of the integral. So it's still going to be ugly, no matter what.
What you could do, I think what he's trying to do, is you multiply the square root of x plus 2 over the square root of x plus 2, which is just literally 1. But that won't help you in this situation. It'll just make it uglier.
You could multiply top and bottom by root x plus 2, which would give you an x plus 2 on the bottom, but now you have a root x plus 2 on top, yes. You have to remember all integrands are expressions. Now, what we can always do with integrals is pull constants out, right? We can pull numbers out. We can't pull x's out, can't pull u's out, right? If there are variables, they have to stay in the integral. But that's a great question. I'm glad someone asked that. All right, 4. Who's going to do 4? Look, I may not even have to put the solutions up. We might get through all these problems in less than an hour, 40 minutes. So this, I can give you a 16-problem test. There it is. Oh, okay. Plus C. Got it. So integration by parts? Okay. Now you didn't put that over here, right? Okay. So first stage was integration. Now, can you explain at all why you went the approach of integration by parts? Was there something when you saw it that made you think, I'm going to do integration by parts, or was it just like, I better try something? Okay. The quadratic in the trig, the quadratic in front, remember integration by parts, I don't know, I keep saying this, I'm not sure. It's getting through to some people, I don't know if everyone's getting it. The integration by parts, the whole idea is that you transfer the derivative. So if I make this my u and this my dv, in the new integral, I'm going to have the derivative of this, which is x, 2x, whatever. And the antiderivative of this, which is going to be sine. So the power on x has come down. And then I do it again, and I can make the x go away completely. So that would be why I would choose to do this technique. There's your ultraviolet minus voodoo. On a test, this is all good. I would like to see the table again, the second table, because you do another integration by parts on this one right here, right? This right here. So I would like to see the table out here just so that I know you're setting it up correctly. And then this antiderivative is pretty clean. So yeah, that looks okay. Any questions? No? Okay. Thank you. 5. Where's 5? Wait, oh, it's right here, right? Mm-hmm. Is this your first one right here? Okay. Integration by parts. Yeah, this is, you got to keep track of these constants because this can throw your whole problem off right here. When you're integrating that backwards, you got to make sure you take that -2 inside, makes a huge difference on what's going to happen out here. Yeah. Okay. Second one's over here. Where's the integral? Hold on, there's an integral sign missing right here, right? Okay, so that's coming over here. Okay, so let's just all make sure we understand that. The 1/2 comes through here, makes this a -1/4 integral, and then you added 1/4 of this integral to both sides of the equation, because the original was right here. So now, look, as far as, again, grading-wise, if I'm looking at this, I really like the use of brackets here. Okay, the use of brackets is good because I can tell that this integral becomes this integration by parts, ultraviolet minus voodoo. I would, if you know it's going to be the rabbit out of the hat type of thing, you should bring the left side down at some point and show the addition, just so that if you do mess up a sign, I have more to work with than if you just, like this jump right here might be a little much, if it's wrong. Okay, but go ahead. So you get that, now what? Okay, on both sides. And then you always throw the plus C on there. With this one, remember, you never really get a plus C because you never really integrate. It's a tricky sort of thing, so you just throw the C on at the end. Are there any questions on this one? Yes. Here, I'll bring it over here. You know what I'll do? Let me bring up something here. What number was this? So here are my solutions to that problem. So here's that integration, that second integration by parts. Here's the distribution of that through here. Here to here gives you the -1/4 of that integral, and then I'm adding the 1/4 of that integral to both sides here. So I have one of these integrals plus 1/4 of the same. 1 plus 1/4 is 5/4. Make sense? Okay, good. All right, what's next? 6. You didn't do it, but you're going to explain it. All right, good. Hold on, let me find it. Is this it? Oh yeah, this problem's weird. It can be, this problem can hang you up right here if you haven't tried it. Go ahead. Okay, so this is a big step, all right? There's nothing that I can say that would stress enough that you can get really lost in this problem if you start going, oh, I'm going to do integration by parts. I'm going to set up an integration by parts. You did later, okay? But I'm saying in the beginning, you might get hung up doing that. You have to notice that the x squared, you're going to try and make that a u. The derivative of that is just 2x. You have x cubed. So you peel one of the x's off so you can create that x dx thing. And when you do that, voila, what's x squared? It's u, right? So you wind up getting the u out in front of the sign, then the u, and then the du was the dx. So I'll let you continue now. And the 1/2 came out. I'm a little confused on this table. What's the issue you run into if you do it this way and you set up your integration by parts? You're already using u in the problem, right? So this table, you can't say u is going to be something in du. You can't, it has to be something else. So let me bring up, which one was that one? I'll just show you the way I did that. So when I got to this part, 1/2 u sine u, I used, instead of u, I used w. So I said w is going to be u, then dw is this, and then it becomes ultraviolet minus voodoo is actually these two multiplied minus these two multiplied in an integral. So that's all. I would just, on a test, I would just make sure you use that other variable if you're going to set up this table. Yeah. The problem is this. What if u was something more complicated than u? What if u was like u squared? Then the derivative down here would not just be du. It only works nicely in this problem because u is u. Like the thing you want to substitute is u. So I'd just be a little bit scared that that might get you into trouble later. But okay, nonetheless, it works out. You set up your little thing here and do your integration by parts, and your new integral, right, is this one. Yeah, 1/2 went through to here. Antiderivative cosine, sine. And then you have the negative 1/2 distributes through. I think we're good. I think we all get it. Yeah. This is it. Yeah, we're good. Yeah. All right, what's next? 7. Oh yeah, this one was tricky. This I don't know. Is everyone ready? Yeah, tell everyone to be quiet. Okay.
Alright, so for number 7, when I started, I looked at it and I noticed it would do a trig substitution, so I tried to go ahead and start and just do a trig substitution, but I ran into issues, so then I started over and decided I needed to do a u substitution before I move along with trig substitution. And I remember, what was it, last class kind of helped out a little bit.
Mhm.
I didn't see it, so I
Yeah.
missed the example and I sat there and messed with it for a minute. And then, because I wanted to get rid of the x squared fourth, I wanted to get rid of that, but I didn't know what I could do, and I remember it said you could multiply 1 into the equation, right? So I multiplied x cubed over x cubed into the equation, which gave me x cubed over x fourth, and then with my u substitution.
Okay, hold on. Let's back up. So when you look at the square root of x to the 8th plus 4, the reason that you cannot do trig sub there is because it doesn't look like x squared plus 4, right? If that was something squared plus 4, then you would be thinking trig sub. The only thing it could possibly be where it would be something squared plus 4 is if it was x to the 4th squared plus 4. And then you would have to replace your x to the 4th with u, yes? So if we try that and we say let u be x to the 4th, the derivative of this, 4x cubed, is nowhere to be seen here, right? The derivative is 4x cubed is not up there. So what you can do is you can force the x cubed to be up here by multiplying the top and bottom by x cubed, right? If I do that, I get x cubed on top, and I get x to the fourth on the bottom. And that, again, not a natural move, all right? Something that we now have in our bag of tricks that we could come in with. And at this point, I'll let you continue. You made your substitution. You had to compensate for the 4 here, right?
Yeah.
So that's why there's a 1/4 out here. Replacing all your x squareds with u, and then the x cubed dx was out here is the du. Okay, so now what about that?
That at that point looked cleaner and matched up to my little table that I could take u equals 2 tan theta.
Okay. So this was just your trig sub. A is 2 and the sub is tangent. And then from there, it just, you replace this u with 2 tangent, you replace this with this, and so what about this? When you looked at that, did you have any idea what to do there?
Split it up. That part is 1 over cosine, and then underneath the sine over cosine.
Okay, so that just, why isn't this just natural log of sine? It doesn't work that way. If it's a linear expression, 1 over 2x plus 1, then it's natural log of 2x plus 1. But if it's 1 over sine theta, it doesn't work that way because the derivative of sine isn't there. Yeah. So 1 over sine theta is cosecant theta. And then you went straight to a formula on your table, on your sheet? Yep. Okay. Let's swap. You can explain the rest. Okay. Where'd you get this information from? The original substitution? Okay. Mhm. Okay, so hold on. Let me just make sure everyone's clear with that. This was the trig sub. U is equal to 2 tan theta. Then this should be u over 2. Yes? U over 2. That should be u, and that should be 2. Then this. This is correct. There's a u in here. That's fine. Okay. So from that triangle, go ahead. Yep. So this is just the ratio. This is your sine flip. This is cosecant, right? Hypotenuse over opposite, and then this one is your adjacent over opposite. So that's cotangent off that triangle with the u there and the side. And then replacing u with x to the fourth, you get that. Yes, that all looks good. Okay, good. We don't even need to take a test. I think everyone's ready. I mean, there's all hundreds right here. My mic's not working. My mic hasn't been working this whole time. No, it is working. All right, what's next? I do have some bad news. We won't be able to do this for the next 2 tests. So this is the only time we'll probably ever be able to review for a test in this class. But maybe it will inspire you to want to make your own groups and figure this out on your own. All right, what are we doing now? Okay, 8. Yeah, I'm glad we're talking about this one. Yes. Good. That's your hidden 0 right there, adding and subtracting negative, or adding and subtracting 25 fourths. Okay? First three terms break up to be these. Go ahead. Mhm. So you have to get like common denominator there and put those together? Yeah. Yeah. What number was this again? 8. Let me see if I did 8. I want to just see where my 8 is. Where's my 8? Yeah, I did the same thing. Let me get to this. This is where you were, right? Let me see. Now, the only difference that we have here is that I have this squared minus, now I rewrote this 57 over 4 as the square root of 57 over 2 squared so that everyone could see that's A. So I have the form 1 over something that looks like U squared minus A squared, and that's why it's not arctan, right? Okay. Now, there are some books that have formulas for U squared minus A squared that involve the inverse hyperbolic tangent function, but in ours, it's formula 20. So if you refer to your book or the formula sheet that you have for that you'll be able to have on your test, it's this 1 over, what is it, U squared minus A squared. So if this is not a plus, 1 over 2A natural log U minus A over U plus A? Or is it plus on top? I forget. Plus is on the bottom? Yeah, okay. So that's the formula. This is number 20. Right? Number 20. Yeah. Okay. So is that it? Let me get back to your work here. So I noticed that you did something a little different. You brought the negative back in, and you changed that to a positive and made this one minus, right? So now your formula looks different. It's no longer U squared minus A squared. It's now A squared minus U squared, isn't it? And there's a different formula for that one, right? It's formula number 19, right? That formula accounts for the switching of those. Okay? So there's 3 different ways you could have done this, all right? All right, so I won't go through that, but we all good with that? Okay, we're good. That's it? Right, you didn't have any other things to plug in, right? Yeah. Okay, because you used the hyperbolic, and you said you used that out of a different textbook, and I don't want to mix that formula into this. Here's what it would be worked out right there. This is what it would be. Question? This is, I'm using the negative from out front here. Here's the formula 20. 1 over 2 times A, natural log of U minus A over U plus A. By the way, I made a substitution in here. You don't have to. Because it's linear and there's a 1 in front, you don't have to make the substitution. I did it just to really stress where this formula is going to come in. Yes?
What if at that x plus 5, what if you let u equal x plus 5 over 2? So
Mm-hmm.
u squared minus a, let a be 57 radical, 57
Mm-hmm.
over 2.
Mm-hmm.
And then you did square root square. So you did triple number. U squared minus a squared.
You could.
Okay.
That's where the formula comes from. The formula that I wrote up on the board, number 20, comes from somebody doing trig sub on this in general.
Right.
Yeah. And so that spits out your formula. Are there questions on this one? I don't think ever use this formula in class. So be prepared for that situation. What you can have on a test, the things that you really want to be prepared for are things like if you have a number over, of course, x squared plus a squared, you know, that's going to be arctan. If you have x squared minus a squared. You can't use arctan, but you can use 20. And if you have a squared minus x squared, you can use 19. All right? Did I forget the negative out there?
Wouldn't have, I mean, like we started with the negative?
Yeah, I think I accounted for it. Yeah, here. Yeah. All right, where are we at? Number 9? Oh, this is the last one? No, 2 more, right? 10 short? Good. Oh, secant. Oh, but it could be made long. I'm looking for 10. Oh, wait, 9? Was it 9?
So I just write everything because I got no memory, so I have to keep track.
No, that's good.
Okay. So the first thing I thought of was linear over irreducible quadratic. So I said, okay, I'm gonna have to do some side. So I got du being 2x minus 7, multiplied both sides by 2/3, and then I got my 2. Then I did the hidden 0 with the 7. So then I have.
Okay, hold on. I'm with you, but everyone needs this needs to slow down. Okay, you have 3x plus 5 up here. You're trying to make it look like a 2x minus 7. Again, I never did something exactly like this in class. It would be like we had x plus 5 in class, and you needed it to be 5x, so you come in with a 5, and it was no big deal. But to turn a 3x into a 2x requires you multiply it by a fraction, 2/3. So you multiply the top and bottom first by 2/3. You said both sides, so I just want to clear that. You're multiplying by 1, and then you pass the 2/3 through here to here. That gives you 2x. But then you have to do the same thing here to here, which gives you 10/3. Yes? Yeah. Yeah. You just multiplied by 2/3, but never accounted for. Yep. So I believe now that 2/3 passes through, which made this the 2x plus the 10/3, which is here. And then you still had the 1 over 2/3 out here, which you flipped over as 3/2. And now you're trying to get the minus 7 to show up there. Everyone good now? I just want to make sure everyone's on the same page. So go ahead, continue.
So I did the hidden 0, got the minus 7. Then I have my 1 over, my u over du. So that's already split. I didn't write it, but it's 3/2 u over du plus the other. I separated it, and I have 31/3 over the.
So 31/3 came from putting 7 and 10/3 together?
Right.
Okay. All right. Good.
All right. So then I went over, check out the 31/3. I have 1 over the irreducible quadratic. I had to complete the square. When you completed the square, you ended up getting.
Oh yeah, there's more out there. Sorry, I didn't see all that. Yeah. Yeah, the copier didn't get it either.
Completing the square was -7. Negative 7 over 2 would have been that second part.
Yeah.
But it ended up being 49 over 4.
Mhm.
So there you go. There's your a squared minus. U squared minus a squared.
Yeah.
And then you end up doing the number 20.
Yeah. Okay. And then the first one we said was just 1 over u du. Any questions on that one? We're good. Good. Yep.
At the point where it's 2x minus 7 plus 7 plus 10/3.
Yes.
You have the du over u.
Uh-huh.
You have to split it up into 2 fractions at that point.
As opposed to
Like du minus 10/3 or whatever over u.
no.
Have to be in the 2 pieces.
Yes. Yep, because all you've done is you've come up with a very tricky way of rewriting what was there, right? That's all you've done. And it's a good question. I don't know an easy way to explain it. It's kind of like, yeah. Well, let's just look at this real quick. Okay. So if I let u be the bottom, 1 plus x squared, The derivative of the bottom is 2x dx, right? Which I have right there. So I think what you're saying is, can you rewrite this like there's du, right? This is du, kind of, but you have to attach it to the dx, don't you? You see? You have to attach it to the dx. So you can't just go put that out there unless you pass the dx through both. Then it would look like 2x dx plus 1 times dx is dx over the 1 plus x squared. Does that make sense? And now you make your substitution here. This is u, this is du, but what's that? See, that's not, this is du, that's not du. It's missing an x and it's missing a 2. It's off by a whole x, so you can't do that. So that's why we have to say, okay, we can do that one. This one, well, we have to find out another way of doing it. Oh, arctan, we're done. Yes. Another great question. Okay, the question is, would splitting it up to start have made it any easier? And the answer is no. All right, so look, if you do this, plus 4 dx, this is what you're asking, right? And this is why I never did this in class. I never split it. Although I did mention why I didn't. It's just, I think sometimes it just goes, and you don't catch the little subtle things I say sometimes, and that's expected. Okay, this one, what am I going to have to do? Complete the square, right? Complete the square. All right, now on this one, I need to make the massage happen, right? So when I do that, I let u be equal to x squared minus 7x plus 4, and then du was 2x minus 7 dx. So can you make this 3x a 2x? Yes, you come in with 2/3, right? I'm doing all the same thing I was doing before, right? Now I distribute it through. When I distribute it through, I'll have 3 halves out on the outside. I'll have the 2x I wanted out here, and then I'll have that stuff down there. Now I still need what? Minus 7 plus 7. So I have to do minus 7 plus 7. The first 2 are going to work with the bottom, but the 7's not. So what are you going to do with that 7? You're going to peel it off, and you're going to be doing 2 of these now. You're going to be, well, unless you're clever enough to catch that you're going to do that one and bring it and let it join this one first. You see that? So my idea is, you know that you're going to have one of these pop out, so just only have 1 pop out. Don't have 2 pop out. That make sense? Who asked that? Does that make sense? Okay. Whatever, I mean, they'll both work. They'll both work. I'm just, trying to show you a shorter. What's that? -2. What are you talking about? No, because you have a 3 halves out here. You see, it's a little more complicated. That 7's going to peel off, but it brings the 3 halves with it, so that's really a 21 halves, and then you add it to 5, and so it is a little more than just putting those together. Okay. Yeah, I don't know if that's all correct as far as numbers. Let me show you. Oh, wait, was that x squared in there? This should be x, not x squared. Let me bring up mine here. Which number was that, 9? That was formula 20. That's the last step. So here's what I got. We did it pretty much the same way. Did you have root 33 on yours? Yes? I'll post my answers when I get them all done. You missed the 2? You had a 31 over 2 out here, right? And then in the formula for this, there's a 1 over 2a. So 1 over 2a should have gotten you, yeah, when you do 1 over 2a, whenever you do 2 times this cancels out the 2. And so you just get 1 over root 33. But then you still had this 2 out here. Yeah, that 20 is getting work, and it should. It's just as valuable as the formula 17. All right, last one, 10. I heard this one was easy. So who's doing 10? Someone told me it was easy. What, was that it? All right, go ahead. Secant to the fourth. Yes. Yes. That's about as clean as it could get right there, you know. Now you could do it other ways, but I don't think they're worth going through because they're more work. Okay, good. That's it. So we have covered all the problems, haven't we, on that review? Are there any additional questions? All right, well, look, you have the weekend, right? Make sure that you review not only this, go back through your homework, you know, go through the problems that I've done in class, focus mostly on integration, right? The stuff that I would ask you, shall we even discuss that? I don't want to leave you hanging because I will put something from the original stuff. What did we do in the very beginning? Inverse trig. Yeah. Didn't we do some implicit differentiation? That's what, when I start thinking of like test problems that would include this, I start thinking things like this, but with like inverse hyperbolic, or, you know, just to show that you know how to take a derivative. Remember, all the derivatives are on your formula sheets, right? For all these trig and inverse trig and hyperbolic trig. Just being able to use them for implicit differentiation is something. Remember that one? Okay. Well, I won't give anything like this. Show that this is this. Remember that weird quadratic we had to solve? Okay. But just one problem, 2 problems from this stuff. The rest, integration. Questions? Yeah, yes, kind of. Yes. You have to designate what you're integrating with respect to. Just like when you're differentiating implicitly, you have to.